Good morrow, fellow humans. My name is Sean and I am obsessed with infinity. So join me as I attempt to unpick the infinity of what is.
The physicist Richard Feynman once put forward the question, quote, "If in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words?" Feynman's own answer was that it would be the atomic hypothesis, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see that there is an enormous amount of information about the world, if just a little imagination and thinking are applied. End quote. So in that vein, take a look at your fingertip. Now, imagine that your fingertip is the size of the room that you're sitting in. Fill the room from floor to ceiling with rice. Each grain of rice is now the approximate size of one of your cells. Now enlarge just one of these cells, these grains of rice, to the size of your room again, and then fill it with rice. Each new grain is now relative to the size of a molecule. And each molecule is now so small that it surpasses the length of visible light waves, and so can't be seen using traditional light-based microscopes. Okay, so far, so good. Now I want you to fill the spaces in between the rice grains with fine grains of sand. This, my friends, is roughly the size of an atom. Another way to picture this is that if we were to increase the size of our atom to the size of the grain of sand, then an equivalent increase in the sand grain would leave it towering at heights more than 3.5 times that of the Eiffel Tower. Indeed, they're so tiny that our bodies are roughly made of 7 octillion of them. So many that if we were to take a human body's worth of atoms and string them up in a line side by side, they would reach from the Earth to Proxima Centauri and back again 4 times over. Now we're going to have to return to the atomic realm a few times yet, so it's probably best that we grasp just a basic understanding of what an atom is. Using the metaphor first put forward by physicist Ernest Rutherford, I want you to now take this atom and blow it up to the size of a grand cathedral. In the middle of this cathedral-sized atom is its nucleus, now the size of a solitary fly. Right in the centre of the hall, buzzing away, one fly. And it is this tiniest of pests which is responsible for 99.9% of the atom's total mass. Whilst bouncing between the various tapestries and stained glass windows are the electrons flying in and around, sort of, what is essentially empty space. Again, sort of. But that can't be right, can it? After all, this would suggest that all elements in this already empty universe, and thus all things, are they themselves 99.9999999999996% empty space. So is all reality merely the slightest haze of an almost non-existent vibrating cloud? If you find yourself balking at this peculiar suggestion, then you may find some comfort in the knowledge that most physicists would be equally uncomfortable with such an artless use of the word empty. For as we shall later uncover, the true nature of empty space, in spite of what many think, is as intriguing as it is complex. Though it still seems that even with a deeper understanding of this emptiness, we're unlikely to ever free ourselves from any amount of peculiarity. What it does mean, though, is that this empty interpretation of both the universe and the atom should only be considered as partially true, a perspective which becomes relevant only in the precise moment when we take our measurement of the subatomic particle. So let's take a look at these subatomic particles. What about the electrons? If the nucleus can be appreciated as being the equivalent size of a fly in a cathedral, how big's the electron? Is it smaller again? Well, yes, much smaller, sometimes, and sort of. When we refer to such particles, we often make the mistake of thinking about them as tiny floating billiard balls. Though what this would then suggest is that these particles should have a definite location in both space and time, just as a billiard ball does upon a billiard table. Though our current understanding of matter tells us a very different story, stating that matter must not only be thought of as having these particle-like properties, but also as having wave-like properties. This is, of course, quite peculiar, as the nature of a wave is something quite different to the nature of a particle, in that it must exist not as a finite block filling a single unit of space or time, but as a movement, a permeation through a medium, evolving its position in both space and time. Unlike the nature of being, which we associate with particles and objects, a wave is, in contrast, a type of happening. If we were to constrain this wave to a solitary moment in time, it may be assumed that its nature was point-like and non-spatial, but when unfolding through time, its true spread-out nature is revealed. So, due to this wave-like nature of matter, we tend to get a few curious interpretations about what an electron actually is, and even more peculiar, what it's actually doing. For up until the moment when we take the measurement of the electron's speed or location, that suggested empty space, which initially filled the cathedral, instead now starts to behave much more like a liquid, as if it was filled with a waving cloud of some sort. This being the wave function of the electron. But the electron hasn't become a wave as you might imagine, as this wave is instead a wave function of probability. And it is the electron's potential location that somehow fills the empty space. And it is the potential location which gives the atom its unique shape, specific to its count of particles and its level of complexity. As things can get a little bit head-scratchy with these topics, I'm going to attempt to illuminate them in much greater detail across later episodes. But just for now, in regards to our descent of scale, we'll continue to focus on the particle-like nature of the electron. For when we do choose to measure its position, it does, as one would hope, and appears in a single spot just as any respectable particle should. The only issue is that it doesn't tend to make things any simpler. For it's a particle so small that not only is it incapable of ever being divided, but it can't even be said that it's taking up any space at all. It's what physicists like to call a point-like particle. In other words, the size of the electron is comically somewhere between the size of the entire atom and practically non-existent. So, there you go. I hope that was helpful. Point-like particles are the smallest things we have ever discovered, believed to host no spatial dimension at all. But though they seem lacking in this spatial dimension, they do host some portion of mass, as well as a certain magnetic influence called spin, which extends into their environment. And electrons also have the ability to both emit and absorb the massless photons that we experience as light. All which seems to evoke a curious question regarding the division between a particle's state of being and its state of influence. But let's not get sidetracked with that conundrum just yet. For now, as they are considered to host no internal structure, they are referred to as non-spatial, and it's in this sense that they're often suggested to sit upon some sort of space-time bedrock, in that they're called fundamental, as if they were the ground floor of matter. So what about that fly in the centre of the atom? What do we know about its innards? Inside the nucleus are the protons and the neutrons. And inside the protons and neutrons are the quarks. A simple trio made of 2 up quarks and a down quark for every proton, and 2 down quarks with 1 up quark for every neutron. 2 unique particles which, remarkably, like the electrons, are not considered to have any spatial dimension at all. Never have we ever discovered anything smaller than these 3 particles. And as such, the up quark, the down quark, and the electrons are considered to be the fundamental building blocks of all matter. Practically everything that is so because of the relationships of these 3 and only 3 non-sized particles. I have to say, this question, how, really seems to be paying off. Okay, but that's matter. Can it be said that anything lies beneath matter? The issue is that at this size, concepts of shape, size, and things need to be re-evaluated. Because in the same way that we once passed the scale of light waves, we have now also passed the scale of matter waves, and thus of things. But there is still, however, a perspective of reality which does pave the way for the particle. Indeed, with a greater understanding of this realm, we shall come to realise that the notion of these particles has been illusory all along. But what could be smaller than non-spatial, you ask? The funny thing is, the perspective from which we can suggest that these particles sit upon something doesn't offer us up a description of something smaller. In contrast, the realm which is said to underlie that of the particles is one that permeates the entire universe. These are what physicists refer to as fields. Invisible fields of force which are everywhere, in every moment, not only interacting with particles but giving rise to them. And it is these fields that also give empty space its intriguing and complex nature, something which we will invest our time into across the coming episodes. However, beyond this scale, at the extremity of the deep dive where concepts relating to both space and time cease to be relevant, we reach the mysterious and all-important Planck length and the theoretical realm of quantum foam. Now remember that this is a perspective of reality that surrounds and penetrates us at every moment and exists at the smaller scale of your own body and is in existence across the entirety of the universe right now. So how big is the Planck length? The human eye can see about 1/10 of a millimetre, or the average width of a human hair. Now enlarge this hair to the size of the entire observable universe. An atom is now 1 light year across, and the Planck length is now 1/10 of a millimetre, the width of a human hair. So now stop and just take that moment for yourself again. The universe that we mere apes have thus far uncovered simply by asking the question how, time and time again, has now been revealed to us as being as big as the observable universe is to a human hair, as a human hair is to the Planck length. Clearly, it's impossible to fully visualize this picture of the universe as a whole, but it's definitely fun to try. The boundless large meeting the boundless small, as viewed from the vantage point of our species, a species who have only within the last 50 years been able to reach their own moon. And I promise you, it is worth it to just take that moment and to sit with the thought. Because it's here that we again find another shoreline in our understanding. Here at a scale so small that space-time becomes impossible to measure, not only physically but theoretically, where the numbers simply fall away into infinity. creating what is essentially a mathematical dead end. Why? Well, because we simply don't have the necessary language required to ask the next right question. Unfortunately, our most successful and prevailing language to date, the digital language of mathematics, simply cannot tolerate the analog nature expressed by such infinities, and thus we're left stranded and confused, desperately wishing away these infinities as we attempt to interpret the riddles embedded within the equations. So what might be a satisfactory interpretation of this mathematical boundary? If these extents are not an edge of reality, could they perhaps be suggesting an edge to space-time? Well, that isn't something that we can claim just yet, but there are a few mathematical theories which are suggesting that gravity, and hence the field of space-time, might be quantized at this scale, and that the relevance of the Planck length is exactly this transition, from ordinary space-time into a world where the fabric is so fine and distorted that ordinary concepts, such as up, down, here, there, now and then, become irrelevant. But it is, for now at least, the very edge of our current agreed understanding. So let's dive in, beyond this shoreline, and take a brief moment to consider the nature of infinity and how it might start to influence our own philosophies of reality. If in this first thought experiment we were to apply the infinity equation to this idea of scale, there may now be a potential for us to consider a perspective where any measurement of size or scale would not be a reflection of deep reality, but instead only a construct of a conscious mind. Okay, now I know that was a leap. Perhaps I should elaborate. Firstly, just consider what we now know about the universe thus far described. The first thing I notice is that the boundaries which we use to define any one material object over another will at a certain level of perception simply cease to exist. There seems to be no ultimate walls present anywhere within nature, regardless of how many times we double or dissect our vantage point in search of them. From our mixed vantages of perspective, which to date have included a blend of microscopic, macroscopic and astronomical perspectives, it becomes clear that any apparent whole, whether it be a rock, a person, a planet, a star, or a galaxy, can always be recognised as both a sum of its constituent parts whilst equally participating as part of an ever grander whole. Each thing bleeds into the next. Now imagine instead a universe bereft of consciousness. A rock would no longer have the prejudice of identifying as just the rock over, say, its identity of the constituent parts, or its grander whole, or even the spaces in between. It is and always has been the one thing. However, we, through the limitations set by our conscious perspective, recognize the rock as being solely a rock, simply because we have an evolved ability to translate electrical interactions occurring at the microscopic level into an experience of touch, when the electromagnetic force of our atoms push up against the electromagnetic force of the rock's atoms, allowing us to sense a false boundary. Touch is an illusion. In actuality, we never sit on a chair. In reality, we only ever float slightly above it. Equally, an apparent boundary is sensed when light photons interact with the electrons of the rock, which then absorb certain frequencies whilst repulsing others, sending electromagnetic waves off into the environment, as little packets of light are then caught by the pupil of our eye, converted into an electrical pulse, then sent directly to the brain, whereby it is then translated into the experience of sight. But beyond the limitations of experience, none of these boundaries actually exist. Reality without consciousness goes from being an infinity of finite raindrops to being an infinite unified ocean. And in being an infinite ocean, no part of it can ever be considered as either small or big compared to the whole. There is, of course, a relative difference between two objects, observed within a restricted finite perspective, but beyond that perspective, any traits of finite individuality simply melt away. The point is that we need to acknowledge that any measurement made within our reality can only ever be considered a measurement relative to two individual finite perspectives that are otherwise made in and of the same unified whole. We shouldn't imagine this infinite expanse and miniaturization of the universe as a type of growing, with the expansion on the right and the miniaturization happening on the left. We instead imagine the infinite smallness to exist everywhere that the infinite largeness does. They're the exact same space, just viewed through different eyes.